Hi everybody, in this video I'm going to be covering an application of pretty much everything we've done so far in this series. So this problem essentially gives us a cannon that's on top of a cliff, and it shoots out a cannonball with a mass of 100 kilograms and force 4,000 newtons. Now we're also told that this planet has an acceleration due to gravity of 9.8 meters per second squared. And what we're asked to find is the resultant force of this cannonball and the equilibrium force. Now they're both vectors, and I'm going to show you how to solve this problem. Okay, so the first thing we can determine is the actual vertical force. And I guess for sake of formality, we'll label these vectors as the horizontal vector, which I'm going to call H, and the vertical vector, which is V, and the vertical vector is equal to 9.8 times 100, because we're given the mass of the object, and we're given the acceleration due to gravity, so we know that the vertical force is 980 newtons. Alright, so we know the vertical and the horizontal, and intuitively we can figure out that the resultant vector is going to be a vector that looks something like this. So that's the resultant vector, and I'm just going to label it real quick. It's going to be FR. Now, from our I guess previous video of vector addition, we know that this is simply an addition of the horizontal and the vertical vector, and mathematically we can write it as such. So the resultant vector is equal to the horizontal vector plus the vertical vector. And I guess to find the magnitude, well, first we recognize that this is just the Pythagorean theorem. So to find the magnitude of this vector, well, we can write it as such. So resultant vector is equal to, or I guess I should, so I guess just the resultant vector there is equal to the horizontal vector, which is 4,000 newtons squared, plus 980 newtons squared. And I've done the calculation here, and it comes out to be 4,118.3 newtons. Okay, so we've figured out the magnitude of this vector. Let's also figure out the angle, and for that we're gonna recognize that this angle here, so that the tan of that angle, the tangent of that angle, is equal to the ratio of 980, right? So SOHCAHTOA, and then tangent is equal to opposite over adjacent, so that's 980 newtons over 4,000 newtons, right? Cross out the units there, and if we now take the arctan, or the tan inverse, we figure out that this angle here is equal to, well, so I guess I'll just write that out there. So that's 980 newtons, or 980 over 4,000, and that turns out to be 13.76 degrees. Now we're also tasked to find the equilibrium force, and that's nothing more than than simply the opposing force that we get from this resultant force there. And so let me just draw that out here. So this right here is the resultant force, or sorry, the equilibrium force, and I'll label that. So that's going to be Fe. And by study of physics, we know that this equilibrium force has the same magnitude as the resultant force, so we know that its magnitude is also 4,118.3 newtons. But what's interesting is that its angle is not the same as the resultant force. Its angle is actually right here, so I'm going to call it angle I guess 2 here, and so angle 2 is equal to 180 degrees, because you see this is a straight line here, and we know that the angle here is 180, so 180 minus this bit right here gives us angle 2. So angle 2 turns out to be 180 minus 13.76 degrees, which comes out to be 166.24 degrees. And I guess this was really just the crux of the question. So we were first able to figure out the resultant vector here. We figured out the magnitude and then its angle, and we used some knowledge of physics to then realize that this equilibrium vector is essentially the same as, well, I guess the magnitude of the equilibrium vector is the same as the resultant vector, and then we just had to compute the angle. That is it, guys. I hope you enjoyed this video, and let me know how I did. And I do apologize, I've got a bit of a flu, so my nose is a bit stuffy. But anyway, thank you for watching, and hope you have a good one.